All right, so in this lecture, I want to go through some reactions of terpenes, some biosynthesis of terpenes, along with the biosynthesis, just a quick overview of the biosynthesis of steroids, so you can at least see kind of the pivotal reactions of these classes of molecules. Okay, so what we do with terpenes is, let's just remind ourselves that terpenes, so I really want to write that as an E-N-E-S. It probably is, and I think I was misspelling it in all the other lectures. Jeepers. Okay, it felt wrong. Okay, so terpenes and terpenoids. Okay, so these are made up of isoprene. Okay, so poly kind of isoprene or polyterpenes. Okay, so there's isoprene. I think I didn't even use isoprene in the introductory lecture. That's my bad. Okay, so we have terpenes and terpenoids made up of isoprene. Now what happens is we actually don't start with isoprene itself when we construct terpenes. We actually start with isopentenyl diphosphate. Okay, so the book shows a nice biosynthesis of this molecule. I'm just going to write PP for the diphosphate. And then this can oligomerize, dimerize, and then rearrange in numerous pathways. It really kind of deeply involves in isomerization. All of these pathways involve in isomerization. So we can start with, this is isopentenyl diphosphate, IPP. This can isomerize to this internal alkene structure, still with the OPP. And this is dimethylallyl diphosphate. Okay? All right, so these two things are actually going to react together to make an oligomer. And so the oligomer is going to have several carbons. If you notice, we don't have any other heteroatoms in kind of this polyterpene unit. So if this is isoprene, we have an isoprene here. We have an isoprene here. And so there are two kind of isoprene units in this terpene structure. Okay, so this is like, I would call this, I see the book calls this a monoterpene, I guess, C10. I'll trust them. I would have called it a diterpene, but that must not be correct. Okay, so we're all learning stuff. All right, so this can kind of continue to react. And this molecule is actually called geranyl diphosphate. We don't want to worry too much about that name. It's just geranyl is a molecule you may have seen in organic 2 and when we did an epoxidation reaction. And so the reason why geranyl is so easy to get access to is you just clip the diphosphate back to an OH and you have geranyl. Many of in geranyl and these types of molecules fall into the class of like essential oils and that sort of thing that you see marketed, and many of them are terpenes. So they have kind of an interesting, some interesting properties. I won't go into that, but we could add another IPP. And after we add the IPP, we actually lose inorganic diphosphate, which I write as PPI and an H+. That's going to extend this terpene by one isoprene unit. And so this is a farnesyl diphosphate. And again, if we want to highlight the isoprene units, go there. Okay, so these chains get longer and longer, and this one's called a sesquiterpene. Okay. Anyway, so this is how we build up a chain of kind of polyisoprene units, which is fundamental to the terpenes. But it's the subsequent cyclizations that really give us some structural variety. Namely, if we take a molecule like geranyl diphosphate, which I just had up, but I want to redraw it in a different perspective. A little bit more of a suggestive perspective. Here again is geranyl diphosphate, which I'll just write as geranyl PP. Okay, so the important thing to recall is that this is a good leaving group. And so what we can do with this leaving group is we can allow it to leave. Why would we do that? Well, when we do that, we actually generate a fairly stable carbocation. And you might be thinking to yourself, rightfully so, why is that a good carbocation? That's a primary carbocation. And we'd be like, it looks primary, but it's deceptive because it's actually an allyl-cation. And allyl-cations are these rare, stable, or not rare, but they're these stable carbocations. So that exists in resonance where you can put the double bond on either position, the exterior part of the molecule. Okay, so let's put it over here. Now what's interesting is that the carbon-carbon bond here in green has double bond character. So there's not that great a free rotation on it. What the molecule actually chooses to do is accept the OPP leaving group back. And I could really, this is just how much I love resonance structure. I'm going to show the arrow splitting the two structures because those are depictions of the exact same molecule. Anyway, so the OPP is going to attack at the internal carbon position, so it's just migrating. Now, why would you want to do that? Well, in doing so, now we've got free rotation about that carbon-carbon bond. And we could just rotate it over here freely because we don't have double bond character in that carbon-carbon single bond anymore. Okay, now what I want to do is lose the diphosphate again. Good leaving group, just falls off. That's going to generate a carbocation that looks eerily similar to the one we just drew. Right, doesn't it look like the carbocation in the upper right? Well, the double bond, the CC single bond as it's drawn that has double bond character is now has the opposite orientation. It looks more Z-like than E-like. Okay, so what we can do at this point is pretty cool is if you want to draw a resonance structure showing this, you can, but I'm just going to take the pi electrons and add to this position that's 1, 2, 3, 4, 5, 6 carbons away. That's going to give rise to this species here where we have a positive charge at this isopropyl unit. When I did that addition, I pushed the electrons over. I'm sorry, that is not a legible arrow. Let's get this nice and big. Okay, I'm going to push those electrons over here to make a double bond at this position. And now that hydrogen, excuse me, that positive charge is looking for something to neutralize it. And it can take a hydrogen from over here. And this gives this structure. Now, why would you do this? Well, if you do this, you get a molecule called limonene. This is a molecule that in organic one, which in the organic one version that you all took, I'm sure, we did a steam distillation of orange peels and isolated a molecule. It smelled kind of rubbery, and it was limonene. Now, it turns out that this hydrocarbon is produced in nature as a polyisoprene from the, quote, monoterpene geranyl diphosphate through the process I've shown here. So here's the biosynthesis of an actual terpene natural product, limonene. And as we have enzymes facilitating all of this, we can actually set the stereocenter at this position. It turns out you can actually get both stereoisomers resolved pretty easily. So anyway, that's an example of first making the long extended polyisoprene chain and then letting it rearrange on itself to get the interesting structure. So this is how terpenes work. They make the long chain and then we allow them to rearrange by some other biosynthetic pathway to get to the interesting natural products. And there's a huge range of structures that can result from these isoprene units. I mean, it's even hard at this point. Like, how do you trace, how do you find the isoprene core of all of these molecules? It's a little bit difficult. I've highlighted it there in green so you can see the bonds that were made as we connected the isoprene units together. Okay, so what I want to do now is wrap up by talking about the kind of hugely interesting transformation to give rise to the ABCD ring system of steroids. So if you recall, we have our steroids, and our steroid core has A, B, go up to C, 5-membered ring to D, and we've got, I guess I have my wedge is stretching across the notes. Sorry about that. And then we do CH3 up here, sorry. And then CH3 is up there in many cases. I feel like I had H. H is alternating here. I'm just going to, well, no, I've got the structure right here. What did I give you before? Yeah, so that's okay. Yep. Down, up, up, down here. Okay, so now we have our A, B, C, D ring system. We have some oxidation at this site. And this is typically an R group. Okay, so what I want to do is I want to take the molecule, I want to go retrosynthetically, so back in time, to the precursor of this molecule, and we get the molecule squalene. I'm going to draw squalene as a super crazy structure. So 6, 6, 6. Now squalene is going to be the biosynthetic precursor to a specific steroid, lanosterol. And lanosterol's got like some of its R group is defined. It's got maybe a couple of extra methyl groups, but the general idea is the same. All right, how did I do? The answer is okay. Okay. All right. So this is squalene. Okay, so squalene is a pretty cool molecule because let's dissect it a little bit. I mean, this is just, after what we just talked about, all right, I lost a methyl group here. You can check that you got the structure halfway right because you've got to have isoprene units at every stage. So squalene is a terpene. But Willoughby, you just said we were making steroids, which is a different type of lipid, and now you're back to terpenes. Well, squalene, the precursor to our steroid core, is a terpene. And I highlighted in green all of the little isoprene units. Sorry, I know it's a complicated structure. The isoprene units help remind us, for example, when we drop a methyl group. Okay. All right, so this is going to undergo a super cool reaction. The first thing that it does is it goes through an epoxidation reaction to make squalene oxide. Maybe you still need that structure. Squalene oxide. So squalene oxide is going to have, we're going to take this alkene and we're going to stereoselectively epoxidize that position, that alkene. And then we're going to treat that alkene with an acid from an enzyme. To give us this protonated like epoxide, which protonated epoxides are fairly basics, or excuse me, fairly acidic. So is the molecule resting, sitting there as a protonated epoxide? Probably not. It's probably hydrogen bonding. It's definitely hydrogen bonding to the enzyme. Okay, so this is where we start. Now I need to bring this molecule back in front of us. All right, squalene again. I'm pumped, I'm excited to draw this again. Okay. So 6-member ring, double bond here, epoxide here. I mean, if this isn't advanced organic, this is, you know, we don't have a biochemical unit to advanced organic chemistry without the squalene oxide cyclization. And this is where all of the tuition dollars get valuable, right? Or something like that. Okay. So I'm now going to go R group here. All right. So this is now squalene oxide protonated by an enzyme. All right. There's a series of steps that occur. I'm just going to show it as one sequence of arrows and then press the end button to the lecture. In the book, they detail each of these steps because they have a copy and paste feature in their structure editor. And I know you do not, taking notes. So we draw this once and we draw all the arrows and we tell ourselves this doesn't happen in a concerted fashion. This happens in a stepwise fashion where each step occurs separately. Okay, so we're going to allow this double bond to add here and bust open this oxygen atom. That's going to leave an intermediate with a positive charge here, which gets attacked by this alkene to leave a positive charge here, which then gets attacked here, I believe, 1, 2, 3, 4, 5, 6, yep, here by that alkene. And that really leaves a positive charge at this position. Am I good at that? Yeah, positive charge at carbon 13. Oh, I don't want to draw that yet because you know I'm not drawing each step individually. So that then becomes positive. And then we go here where we get a positive charge here. Okay. Now the outcome of this is a steroid. We have oxygen here as an OH now. We formed the A ring with 2 methyl groups present. Now an enzyme is involved in every step of the way, so these stereocenters can all get set, but we're going to have CH3 up and hydrogen down. You could draw some interesting cyclohexane transition states, thinking about, you know, chairs and that sort of thing. And this is going to, so this is going to do this, and then it's also going to minus H plus with a double bond rearrangement. The double bond rearrangement is going to give us here. So we're not going to worry about that double bond rearrangement, but just hopefully you can appreciate the interestingness that happens. So an H plus, and it's going to be an H plus from, well, I'll draw the stereocenters, then we can worry about where that H plus comes from. But because we build, because we built our squalene oxide from a terpene, we're going to see kind of this regular arrangement of methyl groups, because it's, and that's kind of present in a lot of these steroids, and which is why you get this kind of similar feature. So it's really remarkable that we see all of this stuff happen. Okay, so there's just a series of H plus migrations that ultimately give rise to that H plus being lost and the double bond being formed at that position. But anyway, this is the molecule lanosterol. So I'm going to stop the video here, give you a second to pause it if you want to catch up writing that structure down. But because we start with the terpene in every case, we're always going to get kind of this regular arrangement of ABCD rings with these methyl groups scattered throughout, because we can't just like not have the methyl group on the terpene unless there's like a migration event that occurs. Okay, so anyway, that will do it for this foray, I guess. Looks like we do migrate a methyl group. Yeah, we do migrate a methyl group. Okay, cool. Anyway, I'll leave it be at this point. So we also migrate a methyl group. In my edition of the textbook, this is discussed in excellent detail on page 167. I wanted to end this one now, not to go into too much detail, but that'll do it for this week's series of lectures on chapter 3. Okay, have a good one, everybody.